Okay, so let's start a seminar. My name is Sun En Zhuang. I'm a faculty here, and it's my great honor to introduce our speaker today, Professor Nick Holonyak. Nick was born in a very interesting town in southern Illinois called Ziegler. He can tell you all about the town. He came to University of Illinois where he got his bachelor, master, and PhD degrees all from this department. And actually his PhD thesis was done with Professor John Martin, two-time Nobel laureate in physics, for the work on transistors and superconductivity. So after his PhD, Nick went to Bell Labs, where he worked for a year, and he conducted pioneering research on transistors. In 1955, he was drafted to join the U.S. Army. And actually, he was stationed in Yokohama, somewhere in Japan. In 1957, he joined General Electric, GE, in Syracuse, New York. That's where he made the world's first visible semiconductor lasers, LEDs. And then in 1963, he came to our department, where he has been a professor since then. And he continued to pioneer a lot of topics like quantum wave lasers, impurity disordering, oxidation processes. And he has received many awards, including Medal of Science, Japan Prize, being elected to National Academy of Science, National Academy of Engineering, and actually next month he's going to receive this Frederick East Medal, which is the highest honor in the Optical Society of America. So today we are fortunate to gather here to listen to the first-hand story from Nick. So let's please join me to welcome Nick and congratulate him on his award.
Thank you, Shunlin, and good afternoon, all of you. I have a little bit too much material for one seminar, but so what? In some places I'll scurry through, and maybe someday we can pull out some of these pieces and have some other seminars. What I want to do is I want to go back to the transistor, and I want to come from the transistor in the direction of the light emitter, lasers and LEDs, and show you what some of the connection is between the transistor and the fact that there's today a light emitter. We're going to go over a span of a number of years, a half a century, 50 years, something like that. And I want to start with John Bardeen here when he was about 80. And this is one of the 20th century's greatest scientists. The only two-time Nobel Prize winner in physics ever, and one of only 4 people that have ever gotten a Nobel Prize 2 times. Madame Curie did it in chemistry and physics. Linus Pauling, one of his was a Peace Prize. And after John, a chemist got a second Nobel Prize. But it isn't Nobel Prizes that matter. You look at that face carefully. That isn't just a physicist and a great physicist and a great scientist and engineer and inventor. That is also a humanitarian. John would be struck in horror at what the world is doing today. Not scientifically, but people to people. Where I'm standing now, there used to be a platform. And John stood right here in 1965 and was telling the audience about the transistor. And he's holding up the tube, the vacuum tube. You get some size, picture of the size in comparison by looking at his hand. And up to a certain point, he lived in some, not in fear, but he feared in a certain sense that the transistor would not, it was important, it would have certain use, but it would not be able to displace the tube necessarily because it was so cheap. And you see, electronics up to the point where I was a graduate student was the vacuum tube. Now, in 1951 when he came, around down the corridor and around on the north side, on the west corridor, there was another seminar room, and he gave a seminar that I'll never forget. I sat somewhere like right here, and John had this box. There were only 3 of these boxes that existed. He had one, Walter Bratton had one, and Bell Labs had one. Not Shockley, Bell Labs. And right here is a transistor. This is the first transistor we ever saw in Urbana. This transistor right here is an oscillator, and John could key this board. There was a little reminder here, and John would play How Dry I Am and stuff like that on that keyboard. And then if he wanted to amplify the signal, well, he could feed the signal into this loudspeaker, and if he wanted to amplify it, he'd just kick this switch over, and another transistor here amplified it. This thing is different than it was then because he had a toggle switch here. He asked me to remove that because he didn't want people to leave that toggle switch on. And also, a capacitor got broken back here, and I'll show you this from the back side. Here's that oscillator transistor, and here's the capacitor I replaced. And you see all these components. For you old timers, you'll recognize the kind of components we used in building electronic circuits with vacuum tubes. Now, he gave many seminars to us over the years. I never tired of hearing him give us seminars on the transistor. I heard a dozen or more seminars on the transistor, but always some facet revealed itself because of certain questions and certain change in times. Something more would become revealed in some sense. So I always learned something, even though I was hearing it another time. Maybe I'm obtuse and don't learn very fast. But at any rate, here was one of his slides. He and Walter Bratton, had done the following experiment. John was a master in understanding the surface, and he knew that there was an inversion layer on this surface of silicon. There's an N-type layer here, an inversion layer, a channel, and they put down a point probe here that is insulated, and the point contacts are here, and there's a spreading resistance here. When electrons are extracted up this way, and they're flowing in there, there's a radial resistance here, and they put an electrolyte here, and when they modulated the voltage on electrolyte, that modulated the conductance of the surface layer and modulated the behavior of the device. In other words, a signal here resulted in an output signal here. This was the first amplifier with a semiconductor. And you notice something very interesting. He didn't call it a transistor. This is not a transistor. This is an amplifier. It's a field effect device. John, when he was interviewed about these things, never called this kind of stuff a transistor. The transistor designation comes from something further, which we'll get into. Now, he knew and Walter knew about germanium, and they moved that experiment from silicon to germanium, and they put this gold pad here to try to get rid of the electrolyte. The electrolyte was slow, and that was not a good amplifier. So they put this pad here thinking it would be on the oxide and modulate the surface conductance underneath the oxide, and Walter was trying to open up a hole here where he had put the point contact for the spreading resistance, and some accident occurred. There was some spark or erosion or something, so Walter moved the point contact out to the side. Ignore this. You didn't have germanium to burn. You didn't reach in your pocket and get some more. You didn't go into the cabinet and find some more. There wasn't much. And they used the same piece of material over and over. But at any rate, Walter moved the point out to the edge. And it's typical when you do experiments like this, you change your bias. So the thing did not work as a field effect with the bias that it should have had. It worked as something else when they reversed the bias and they knew they had something else. They had what no one knew was that when the gold pad was put on the oxide, it would not be on an oxide. The oxide and germanium isn't all that good. They were in direct contact with the germanium. And they had an injection device. A signal on one of the electrodes gave a signal in the other electrode, and they realized what they had. So they quickly then built this thing here, same piece of germanium, which is ingenious. Think about it. You can't go run around and get another piece. But you can do another experiment on the same piece of material. The piece of germanium is on a block, and we'll call that the base. Here is an insulating wedge, and they wrapped the gold strap around it, and Walter split the gold right here with a razor blade underneath. So he had one electrode over here and another electrode over here. One turned out to be the emitter, one turned out to be the collector. Low impedance input on one of those electrodes resulted in a high impedance output at about the same current level on the other one. Transfer, resistor, transistor. Here's the first transistor. Incidentally, Bardeen signed this at a later point when we managed to get this picture. And you can see how experiments are done. This is a spring clip, which is a paper clip opened up. This is a marvelous thing. You know, this was reproduced a couple of years ago in the movie Transistorized. The piece of germanium, incidentally, came from here in Urbana, from our lab. But this thing worked something like 50 years later when it was done again. A good 50-year anniversary experiment. Now, they quickly realized that they didn't have to do things quite that way. They could use the normal point contacts of things like crystal detectors of World War II fame. And so here's a point which John, I found out in a later conversation with him, named the emitter. And here nearby is a collector. And here you put forward bias on this emitter, and you inject holes. Now, when you inject holes in this N-type slab, electrons relax to try to compensate that charge. Dielectric relaxation occurs. And those holes diffuse and try to move over to this collector. They're injected at low impedance, they're collected at high impedance, gain. Now we have a transistor. Now the word can be invented. And as I said, John Bardeen invented these terms, emitter, collector, base. He was a great physicist, but he also had started with a bachelor's in electrical engineering and also a master's. And so he also was a great engineer and understood what was going on. And Walter, who was a good experimentalist, was a great experimentalist with John around to guide and interpret and so forth. And John always looked at the data. He didn't listen necessarily to just the talk around him. At any rate, there's something very important here. As he pointed out in his last interview with NHK television, it was known that heat increases the electron-hole pair population in a semiconductor. It was known that light does, but it was not known that current does. So the injection phenomenon comes from here, injection, where holes are injected into the substance and electrons relax in and you've got a population. Now the two are going to annihilate one another. While the holes are diffusing over to the collector, the electron is trying to annihilate the hole, and it's either going to generate for you a photon or it's going to generate heat. Aha, this is interesting because we now have a mechanism to explain why current-driven pieces of semiconductor emit light, because now we can understand what this phenomenon is all about. So it's the transistor that taught us about injection. You would have no light emitters without that. Now, there's one ambiguity. Since John was a master of the business of the surface conductivity and surface channels, you could raise the fact that maybe there's a channel up here. But an interesting thing happened. There was a man by the name of John Shive at Bell Labs, and John Shive did this experiment again. He took a wedge of germanium, he put a point contact on one side, then he put a point contact on the other side, and the surface channel was long, but the path internally was short, and the device works exactly like Bardeen and Bratton's device, and Bardeen knows immediately that it's a bulk effect and not a surface effect, whereupon Shockley had to jump up and reveal what he had been writing down secretly in his notebook. This experiment was not done, the Shive experiment, to prove Shockley's p-n junction theories. It was done to try to see what the channel was doing, and Bardeen knew right away about injection, apart from anything about dealing with p-n junctions. But as a matter of fact, the p-n junction was known. And right down the hall from us in room 141, 15 years ago come this spring, Bardeen lectured to us, those of us who took his course, on semiconductors and transistors. And he always used this diagram. This is his diagram. I'm using it as I did the other slides of his. The only thing I did was put this H on here for holes and this E on here for electrons, and I added this line here which indicates there must be some kind of a transition here from N to P. Now, I don't care if you understand anything about surfaces and all that. This is the equivalent of a p-n junction. And when you forward bias this thing, these holes here are emitted from the P layer here into the N material here. It isn't just electron flow across the top, as was the case before Bardeen. Bethe, Schottky, everybody else. And when Bardeen told us this, he's holding his notebook like this, and I'm sitting where Professor Zhuang is sitting, and he turns and looks over here, then he looks at us and he grins a little bit. He was a shy man with great humility, and he grinned a little bit, and he said, and he pointed at these holes, and he said, if Schottky had looked here to see what the holes were doing, the transistor would have been invented. Figure it out yourself then. Who invented the transistor? Now, the transistor then as a junction required 2 years to learn how to build. We build these things easily now, but then you don't know how to do this. And so I've jumped from germanium to silicon, and this is a Bell Labs alloy transistor as of 1954. Gold with some antimony in it has been used to dissolve some silicon here and here. This is p-type silicon. And then when you freeze the system, the gold that you've dissolved regrows on the parent crystal, on the mother crystal, and it grows n-type here. This is p-type. This is, I think, bigger. This is the collector. This is the base. And the same thing is happening here, and here, this is the emitter. There's a lot of problems here. You can't build from two sides very well and reference very well, and how do you make these dimensions and geometries and everything right? It's almost impossible. Here's a similar device, and actually there was about 1 micron here. This is totally accidental. If you set out to do this, you would have to build maybe 100 of these or 1,000 of these, or have technicians that you could wear out doing it to make this dimension thin. This is not a good way to build anything from both sides, unless it's a thick device that you want to build in the first place. But transistors want to be thin. So in the middle 50s at Bell Labs, something happened. There were people around like John Mull who were great, big thinkers, and John knew we had to work on silicon. So did Bardeen. Bardeen had written that in his notebook before I was his student. And is that focused right? I don't want to mess around with the focus because I'll fool around and get it worse. But at any rate, this is a transistor built top down, all from one side, reference from one side, not two sides, one side. And it's a p-type crystal. Antimony or phosphorus have been diffused in and give us an n-type region here. And then the ring base has been metallized by evaporation onto the connection here. And then aluminum metallization has been done on top to make an alloy, a thin alloy junction. It was in John Mull's group that silicon was first metallized. No ICs without metallization. You're looking at the first metallizations. And when we did this diffusion and did the N layer here, on the back side we had an N layer. If we put it together that way, we had the PN-PN switch, which was what we were trying to build, switches for the switching system. And it was Shockley then who decided those switches, and there's a long story there, would be the mechanism for him to get rich if he set that up on the West Coast as he wanted to build switches. There would be a lot used in his mind, and he made some fundamental mistakes, and it didn't work out that way. Here's another view of another one, and this one's in color and give you some idea of what we've been talking about. At any rate, there is a direct path from these things I'm showing you now, just these two slides, to what today you call an IC. Because this technology is the basic technology that went from John Mull. There's a nice, those of you from MIT and have MIT connections, ask them to let you see the 1992 John Mull seminar videotape. And he will explain to you how this technology was handed to Shockley, how it was used to build Shockley's company, and how then it spilled out to become the transistor technology that became the IC. The story is not like the Swedes tell it. It is different. And at the time the technology is going to Shockley in the West Coast, I wind up, as Sean Lin pointed out, as a soldier in Japan. And Bardeen introduced me to the science establishment in Japan. This is Kikuchi at the Electrotechnical Lab. I am showing him this technology because Bell Labs lawyer said I could talk about everything I was involved in, but I could not talk about the oxide, the protective oxide that is used in ICs and everything else, and it's fundamental to the integrated circuit. At any rate, you can see the date on this. Kikuchi later became, for 15 years, the director of Sony's research laboratory. Now, and a little bit later, people are trying to thin these transistors because they're thick and you've got too much collector resistance if the slab is too thick. So what you do is you build the material you want to build a transistor in by epitaxy on a highly conductive slab. In other words, epitaxy is needed for transistors. And at the same time, we are also, those of us who know something about negative resistance, are enamored with tunnel diodes. And so here's a silicon tunnel diode. Again, the alloy process, it's local electric phase epitaxy, which was invented by Bob Hall at General Electric in Schenectady. And from 1950 to 1960, the world's transistors were made by Hall's nice simple alloy process. TI alone claims that they made 1 billion alloy transistors. If you were an electrical engineer like you guys, all of you folks here, men and women, and you were going to work with transistors in the period I'm talking about, you couldn't afford them unless the alloy process existed. That was a great thing that the man did. Here's single crystal, and you can tell it from my flat junction, and here's polycrystal, and you can see my regrown region. Now here's, for those of you who know something about tunnel diodes, this is how they look. Here's current vertically, here's voltage this way, here's germanium right here, here's silicon right here. Those of you in silicon technology, I'd like for you to build me a better one than this. There's some problems there. And then here's one that goes out further, gallium arsenide. We are already before 1960 enamored with 3-5s because we can do certain things with 3-5s we can't do with silicon and germanium. And not only that, we have problems with reliability, and so we would like to have other ways to make these things other than alloying, and we would like the voltages to go out further. In other words, what if I could put some phosphorus in for the arsenic and run the gap up further? Could I push this IV characteristic, this injection characteristic out further here to the right? You see, in other words, these kind of things enamor us. So we get involved in epi because of the transistor. We get involved in it because of stuff like this. And here, just as a matter of convenience, I want to show you the way epitaxy was first done in 1960, 61, and so forth. You put a substrate here, and you put the ingredients for your epitaxial material over here. You raise this to higher temperature. This is at lower temperature, and you grow whatever you think will grow. Incidentally, this is before there is a semiconductor laser. And here's one of the things we wanted to grow, gallium arsenide on germanium. There's an N-type layer here. This is a wide gap emitter transistor. Here's another case, gallium phosphide on gallium arsenide. This would be a high-efficiency solar cell. And I'll skip this and jump over to here, gallium phosphide on gallium arsenide. I want to show you this. And then here's something interesting. Here's gallium arsenide phosphide of one composition, N-type, P-type, on N-type gallium arsenide phosphide of another composition. We know about heterojunctions. In fact, we're trying to make them. The people later who say we need heterojunctions for lasers are not so prescient, so forward in their thinking because this is already being worked on. But it needs a lot more work. And so there's a contribution. Now this man came to visit me in 1961 when we're doing this work to talk about this stuff. And this is a picture of Syracuse. The man is Hilson. For those of you who work in 3-5s, I beg you to go to the library and take a look and see the earliest book you can find on compound semiconductors and compound semiconductor devices. This Englishman, Hilson, you will find is probably one of the first authors. And also he was involved in the business of the gun effect oscillator. All right, now so here then, 40 years ago at LA, we reported gallium arsenide grown on germanium. Gallium arsenide N-type grown on P-type gallium arsenide. And again, for those of you building devices, I'll let you and some of our students worry about why these scratches here are deeper than the same scratch here. And on P. A tunnel diode. Now this is one that's really interesting because we didn't have the crystals to work with, and so we used anything we had, junk. And here is a piece of gallium phosphide that's polycrystalline. Here's a crystallite. These are scratches that are in here from cross-sectioning. Here's a crystallite, here's a crystallite, here's our surface. And when we grow the epi on there, here is the epi material, but what I'm really pointing at is this arrow and this crystallite that propagates here. In other words, it's epitaxy. It's single crystal that grew on the mother crystal. Even though the mother crystal is poly, there's some single crystalline stuff in there that you can see says to the crystal that's growing, grow oriented relative to the substrate. And then here is something that I showed you on the diagram. Gallium phosphide grown on gallium arsenide. There's an intermediate gallium arsenide phosphide layer in here. In other words, we know about alloys. And I want to point out something further. I'm a junk collector, so this is in my junk. And this cross-section was done in 1961, but my graduate student photographed it again in 2001. This is 40, you're looking at a photograph made 40 years later. It was made in 1961 once, it was made again in 2001. In other words, again, heterojunctions and alloys and so forth before there was a semiconductor laser. But this is a material that goes up to higher energy out of the infrared into the red. And so when it looked like we could make, well, here's the material again. Gallium arsenide phosphide grown on gallium arsenide, and in the cross-section with visible light we could see through it. So since we know how to build things like this, in 1962 when it looked like it may be possible to build a semiconductor laser, in the group I was in at General Electric, we knew how to make gallium arsenide phosphide. The rest of the world didn't. They had some crazy ideas about how to do that, but we knew how to do that. We knew how to do it, and we grew gallium arsenide phosphide, diffused a junction in it, made a mesa here, and you're looking at the first alloy device ever. In other words, it's an alloy. It's not germanium, it's not an element, it's not silicon, it's not an element, it's not gallium arsenide, which is a locked binary. It's a ternary. It's an alloy. And maybe it's junk, but if it is good enough to be a laser, it isn't junk. This is the first proof that the 3,5 alloy had device possibilities, and it's important because today you cannot build many lasers and LEDs without alloys. It's not possible. It won't be very good. Here's another view that may be better for you. It's a blown up view. See, here's that slab. You can't see very well. There's a Fabry-Perot face polished here and here, and this lead got bent. This is the lead bringing in the current to the P-type region, and this is an N-type crystal. And here's the output from the mesa. It's a laser, and another one of its mates looked like this. Our publicity agent worker drove me crazy at our apparatus, wanted pictures. And I tried to get rid of him, and I swore at him pretty healthily. But finally he persuaded me. And see, these lasers were running filamentary, and so there's a spot right here where the film is being overexposed because of the brightness of the laser. And the beam is diffracting out of that spot, and the part that's bouncing off the TO18 header is reflecting up, and so the true pink color of the laser is here, whereas this is overexposure of the film. This is the first 3,5 alloy visible device photographed by its own light and not converted. This has been published many times. Now, at the time we did this in 1962, some external people, it was a secret, but then the secret, I broke it, and GE broke it by inviting and having a conference for the military, and John Bardeen stopped in to see it. John had thought about lasers but didn't know how to build them. And so he stopped in, but it was a Saturday, and we couldn't take pictures. We couldn't get it set up quick enough, fast enough. So about 10 years later in our laboratory across the street in a building that now doesn't exist, John and I are looking at these kind of things, and we're looking at indium gallium phosphide. He invited me to move that work to Illinois because if I could do that in a little group in Syracuse, in General Electric, bright graduate students with a lot of energy can do this kind of work in a place like Urbana, which turned out to be correct. And at any rate, he was alive then, and we were both younger. He was younger then than I am now. This is another view of a Syracuse device. It just gives you a different view of one of our slabs, one of our gallium arsenide phosphide slabs, and you can see the Fabry-Perot face that we polished on the side. And by some simple tricks, not complicated machinery, it's just simple tricks. And this slab now is a kind of slab that you could go in a building where they were putting together diffused silicon diodes. And where the ladies working those lines would have these glass packages with this bent lead here, and they would drop in this open end, a piece of silicon that's a diffused diode. And then they would put this lead in, which has a glass bead, and they could heat it, and this S-spring contacted the diode. But they didn't know if we were putting in silicon or gallium arsenide phosphide diodes. So this is one form of our first LEDs. And I had a lot of these. I handed them out to that group from the DOD, and they carried off all of my first LEDs. But GE did offer these for sale in 1962. So if you wonder where the LED and laser came from and who first put it for sale, here's Bob Hall of Schenectady's gallium arsenide phosphide laser, $650. My visible ones are $1,300. The LED gallium arsenide is $45. My gallium arsenide phosphide visible LEDs are $100 and something. Now the prices, by the time this is in the Alloy radio catalog, in 1965, the price has dropped by 2. And there's a lot of interesting stories about all this. But it all goes back to this, and it's on paper when all this started. Now, when I set out to do these talks, this gentleman here, whom some of you I'm sure recognize, again, we're out of focus, and the focus is bad, but I don't know who's running the machine, but the focus should be better. Am I blocking the view from over here? Okay. Now this is better. Okay. Now this gentleman here said to me, talk about the disordering, talk about the oxide. And I won't bother to identify the other people. You worry about that. And so I agreed with Fing Thong about that. But how are we going to do that? And we have to have progress in going epitaxial 3/5s. And in 1975, this man over here had built this machine. Look at how nice he laid it out. He's got nice electronic valves and all that. I had tried to get Monsanto to build a machine like that so we could do some quantum well stuff. And this guy was building ordinary heterostructures and so forth with this, and reported that and solar cells and so forth at Cornell. And he even had built another version of this machine. And here's the other version, which is more sophisticated. We're looking at the first MOCVD machines that we're worth talking about. These machines grew some material for us, but before we ever did that, we had already, in 1977 across the street, grown, and that machine that I showed you had to be $100,000, $200,000 of stuff. This machine that we grew this in was $1,000, $2,000 of stuff. This is indium gallium arsenide phosphide, these dark layers, grown at about 150 angstrom thickness in a p-n junction arrangement. This is a little piece of superlattice if you want to look at it that way. These are the first quantum well lasers. They're not made by MBE, they're not made by MOCVD, they were made by LPE. They were made across the street. Very clever work of our students. But Dupree and his MOCVD machine could grow better for us. So when we showed the world our LPE quantum wells, Dupree was willing to go into his MOCVD machine and grow us some stuff like this. Here's a thick piece of aluminum gallium arsenide 60%. Here's a 200 angstrom gallium arsenide layer, another 1,000 angstroms of aluminum gallium arsenide. We take the substrate off of this, put it under diamond, heat sink it, photopump it, and you're looking at the first continuous room temperature quantum well laser. Very simple. Lots of data came from this. Now I can go to the machine and say, okay, machine, make me something more fancy. And here's something more fancy. Here is a stack. Focus on this region right here. This is a superlattice. This is gallium arsenide 45 angstroms, 150 angstroms aluminum arsenide, then a stack of material like that. You can, if you take the substrate off, we didn't do a good job over here, but we did right here of taking the substrate off. We look through there with visible light. We see the nice red superlattice. Over here, in about 1980 and a little bit later, we mask these red dot regions, and we, at very low temperature, diffuse zinc into these crystals, and the aluminum arsenide and gallium arsenide, which is in layered form, becomes intermixed. Aluminum is a funny gallium, and gallium is a funny aluminum, and the two can replace one another and intermix. The crystal is still single crystalline, but obviously we have changed the energy gap of this disordered random alloy. This yellow stuff is higher gap than this stuff that's acting red. Immediately invoke the Kramers-Kronig relations, and you know that that's a change in the index of refraction from this yellow region to this red region. And you then have the basis to define lasers, waveguides, all kinds of stuff like that. So this is an important technology, and this is what Professor Feng wanted me to bring to the world's attention. It came from Urbana. And again, nice work of the grad students. Now, sometime later, we put these wafers back into a processing operation, and we put nitrogen gas with some water vapor in it at low temperature, 400 degrees, and something interesting happens. This random alloy, which is about between 70 and 80% composition of aluminum gallium arsenide, this, does not oxidize very fast. The red dot, which is still superlattice, doesn't oxidize fast because gallium arsenide is a slow oxidizer, and so it's blocking the downward oxidation. So more or less nothing happens here and here. But where we have cracked into the edge of one of the superlattices, the oxidation is fast in the aluminum arsenide, and it goes laterally underneath. So from the day one, we knew about subterranean buried oxides. You can't do that with silicon. You don't set up silicon in such a way that you have an edge oxidation. But in the 3.5s, we can set things up so we can oxidize down or we can oxidize edgewise. That turns out to be very important. That is another technology for defining devices. So one way to do this is to make your stack that you're going to make lasers out of. You can cut trenches down, or you can cut mesas down, or you can cut wells down and then do your oxidations. And in this particular case, what we did was we cut a mesa on this side and on this side, and from the edge, we left some high composition aluminum gallium arsenide here that oxidized on the surface, and we oxidized inward to here, and inward to here. This is 87% aluminum gallium arsenide. It's a fast oxidizer that came inward this far and inward this far. This is 85% here, which is a slower oxidizer, and it came inward to here and inward to here. We made an aperture, a buried aperture on edge-emitting lasers. The whole VCSEL community is sure that that came from them, but now I swear it's bullshit. And in other words, the grad students did that a year before them, apertures, subterranean apertures. And this is vital work because it's demonstrating an important technology. Almost all VCSELs use this technology today. All right, now we're back to people again. I'm sure I'm out of focus, but so what? I won't identify everybody, it doesn't matter. Here's Stillman. When Stillman was a graduate student, we took one of our filamentary lasers. He took the laser, and I put this platelet on here. This is a 1 micron platelet of CAD selenide. And we use the filamentary laser that's putting out at this wavelength, which is shorter wavelength. We're using it and stopping that, grabbing those photons, and generating cadmium selenide photons. And this thing is emitting off the front surface. We didn't call that a VCSEL. We called that a volume laser, volume excitation laser. And while we're doing this, Bogdankevich and his people in the Soviet Union are e-beam doing the same thing with electron beam pumping. And 1 year before us, a group at Lincoln Laboratories took indium antimonide, and because you can inject deep in indium antimonide, you can polish facets and make a volume emitting laser. And so in modern times, the VCSEL has been rediscovered. It's funny how modern workers don't reference older workers having come in and added further to the technology, but not having originated it. At any rate, I need this for a different reason. I want to show to you that I use light to generate light. Okay? And so now I've changed this a little bit. I cleave this edge off to make this a reflector edge, and I cleave this edge off to make a reflector edge. And instead of using a light beam that pokes into the crystal, into the surface like that, I want to use a laser here, and we had lots of them, that would emit broadly here and drive this system across this dotted line here. In other words, this doesn't really operate this way, it operates coming out this way and coming out this way. And if you check my numbers, check my wavelengths, check my numbers, you'll find we're talking about an energy gap here of, okay, we've got an energy gap here of about 1.8 electron volts. This is a little bit higher, this is a little bit lower, there's only 50 millivolts loss here. In other words, I'm very efficiently grabbing photons and making photons. And so I know that there's a difference in the chemical potential of electrons in holes on the inside where this is happening that's of the order of 1.8 electron volts. So I should be able to reach in there and grab 1.8 electron volts of little battery. But if I try to hook onto the crystal here to do that, it won't work. On the other hand, if you let me make this N-type up this way, having made it N-type, it can't be P-type, it's N-type now, I can grab on to that chemical potential that I've set up here with light. And similarly, if I make this p-type, I can grab onto that whole chemical potential on the other end, on the other side. And so now I can grab onto that, and I can give you this voltage. I can give you this 1.8 electron volts. And I can also take a battery, take a source here at 1.8 electron volts and hook it around here, put it in opposition to this, put a switch here, close the switch, and nothing happens. No current flows because my outside voltage is just equal to my inside voltage, okay? But now if I turn off my light source, my outside voltage maintains the voltage and my laser still operates. What I have done is subtly seduced you into a proof of the fact that an ultimate lamp is a p-n junction. You can't do better. If you want to read the argument in detail, go look at September 2000 American Journal of Physics. In other words, I have proved to you without going into great detail that the p-n junction is the source of an ultimate lamp. There may be others. Well, now that I got ultimate lamps, I'm off and running. I'm not wasting my time then. I told you about indium gallium phosphide. If I go into Dupree's machine, I can turn that into aluminum indium phosphide because aluminum substitutes for gallium. They're funny replicas of one another. So we can go into those machines, grow aluminum indium phosphide, grow aluminum, substitute aluminum for, or substitute some gallium in here in aluminum and make this lower gap, and then do the same thing on the top side as on the bottom side, and we can make a heterojunction light emitter, and you look at them every day. This is on gallium arsenide, so there's some problems. This diagram came from Fred Kish and Crawford's group at Hewlett-Packard, which became Agilent, which became Lumileds. And Fred drew me a nice diagram over here for his purposes, which says that if I generate an electron hole pair here, and I want to take this electron hole pair out of the top and make a VCSEL, if I want to take the electron hole pair out as a photon out of the top, I only have a certain escape angle because that's high-index material. That's a box of high-index material that's trying to trap my photon on the inside like a fiber optic does. And so I only have a certain escape cone. And out these edges, I only have a certain escape cone. But now, if I'm a laser guy, I build some Q reflectors into the top and into the bottom, and I make a VCSEL. If I'm an edge emitter guy, I build myself a waveguide across here, and I've got a long cat length, and I got a lot of gain, and I build myself an edge emitter. In other words, stimulated emission solves my problem of how to get all the photons to go out the top or out the sides. And so you get high efficiencies. Now, Fred points out that some of my spontaneous photons get lost in this absorptive material. So he does a nice experiment. He described this here some time ago. He grows his structure, or the people that grow the crystals grow it, and then when he makes his LED, notice, you see the LED is bright where he has this nice material on top, but it's dim where you have the gallium arsenide on the bottom. So what he does is he takes the gallium arsenide off, splices it with some nice tricks, nice inventive tricks on the gallium phosphide, because you want to do this big, you don't want to do it small if you want to make money. And you wind up with this, and now look at his LED now. We don't have to do physics, we don't have to do engineering, we don't have to do equations, but look, this is obviously much different than this. And another one of the gentlemen in the group, Crames, sees that, well, you don't want to bounce those photons around anywhere too many times. In stimulated emission, you don't bounce them around. You take them, you create a path to take them out and create Q in a resonator. In an LED, you don't want to bounce the photons around. You play around with the geometry and make the geometry so after a couple of reflections, the photon is more or less normal to a surface. And with their great cleverness, look at this external quantum efficiency here in wavelength here. This is red wavelength here. This point is 55 to 60% external quantum efficiency coming out of an LED, spontaneous light. This right away says to me, my whole argument presented many times over to students that p-n junction is an ultimate lamp is right. Unless you want to quibble about factor of 2, but the factor of 2 gets smaller as we go on. Then, if we now look at the CIE curve, what is it, Jean-Pierre? What's the CIE curve? Commission Internationale Éclairage. Some of you people know French. I don't know it, but is that right? CIE curve. And look, if we build light at this wavelength and we convert power totally to light, we cannot get more lumens. Lumens are what we see. That's a factor of how many photons and the sensitivity of our eye, and that's lumens. And we cannot do better than what you are over here. Now, what's good about this thing is this is where your conventional light sources are, okay? You know, you understand what these are. I don't have to explain them. Fluorescents are over here. And look where this thing is, these aluminum, gallium, indium phosphide heterojunctions are. Direct gap. And here's where the nitrides are coming up over here. And when this curve was given to me, you know, years ago, not 2, 3, 4, 5 years ago, so the points are up higher now. In other words, it's clear that the semiconductor is becoming the world's lamp bit by bit. It costs money. But if we look now at time, there's 40 years along here. Here I am somewhere over here in the thing I started with in '62. And we could do a whole seminar along here and the steps along here and all the arguments with high managers in important places. Important places that now are almost at the edge of bankruptcy. And look at this, up, 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 up. And when this curve was first given to me at an anniversary about 3 years ago, this point wasn't here. But there was a box here called the ultimate LED, or ultimate lamp. And as I said, that point wasn't there. And so here again, we start over here and we work our way up here. And there's a lot, as I said, a lot of arguments, a lot of technology that died along the way. Some of this technology has survived. This is logarithmic. In fact, this is interesting because you can immediately say, Moore's law. No, 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 no. Moore's law is just geometrical growth, and it's become what it is because of publicity. This is the usual geometrical growth, and this is Crawford's curve. Crawford is the guy that was running these groups and stuck with this for almost 40 years to push it, push it, push it. And now, thanks to Crawford and others, this curve has gotten up to here. I won't dwell on why this one is going up like this, but this one benefited from these. The technology is the same, the techniques are the same, the thinking is the same. There's some obvious contributions here. And here you look again at where we are with the conventional sources, okay? And so when we get to the top, there isn't anything better than an alloy heterojunction 3,5 LED. The problem is, how do you make them en masse, big, and so forth and so on? So to me, to look at this thing now is to feel differently than you, because I feel real happy because we start with an alloy here, we argue a lot along here, this makes possible heterojunctions, and direct gap semiconductors are what I am claiming over here is going to be over here, and that's what is the case. Heterojunctions and direct gaps and alloy materials is what you are seeing more of and more of in your life. I don't think I have any more slides, but I want to show you something so that I'm not just talking and looking at pictures. I want to show you, this is one of Fred Kish's indium gallium phosphide LEDs with the transparent substrate, with the shaping, the cleverness of the shaping and so forth. This is 85 milliwatts. If this 85 milliwatts were put in the form of a laser and focused into your eye, it's at damage level. This is not damage level, okay? Incidentally, if I show you a blue one, I didn't bring the blue one. If I showed you a blue one, obviously that's higher photon energy. And instead of 2 cells back here, you need 3 cells. In other words, the energy gap matters. So when I was talking about the 1.8 electron volts and all that, that was all tied to the energy gap. In other words, you build me a shorter wavelength photon, more energy gap, and so forth. And when you work with those kind of materials, you suffer more. It's harder to do. Now, one other thing I want to show you is I want to show you this traffic lamp. I want to show you the edge of the traffic lamp. You see, you can look in a port here, and then look in this port. If you look in there carefully, there are 12 LEDs in there, of these special ones that I've been talking about. And now, this thing is about a year or more old. And in the meantime, those 12 LEDs have become one. And so one LED is now it's become a lamp and is your traffic light. And these things last more than 10 times longer than all the stuff that people have been using out here. And the power savings are great. If we're going to live on a crowded planet, we're going to have to do things better. We're going to have to use less power. We're going to have to do stuff like this. In other words, there's no escape from technology. I have only one regret. I regret that John Bardeen is not alive to see what has happened. If he were alive and we asked him, could he see all this, he would say, he'd shake his head slowly, because he was a man of great humility and honesty, and you cannot project with great accuracy. If you said to him, did he see something like this coming, and was it important what they were doing along the way, the answer, he would nod his head, yes. And so if you ask me, where are we going, I can't tell you at the 10-year range. All I can say is there's a lot more of this to do. My body is getting old, but my mind doesn't stop seeing problems to work on. And if I see problems to work on, you must see problems to work on, or else you're loafing or something. You want to, and also I want to refer you back to the Crawford curve and point out to you that's a 40-year curve. You cannot go on some work that we're engaged in and go out and 1 year later be a millionaire, have built yourself $1 million company. You haven't worked very hard, very long to be talking about $1 million. And now that's coming home for people to see. But relative to my regret, I am sorry John is alive, because with the transistor, great things happen. The electronics you see today is not the same electronics as you could do with a vacuum tube. It's just not possible to do with a vacuum tube what is being done. And even though some of this stuff is expensive, it gets cheap. So there's a lot to come from this. There's a lot further to do. I thank you for your patience. I've said about all I want to say, unless you have some specific questions you want to ask me.
Okay, couple of questions over there.
Yeah, nowadays most transistors are
Most what kind of devices?
Most transistors.
Yeah, but then the other one.
Optical devices.
Optical, yeah. Okay.
They are gallium arsenide. However, people are trying to integrate now optical devices, electronic devices, to make better integrated circuits. And there are two solutions to do that. Either take the gallium arsenide optical devices and throw them on top of the transistors, or to make silicon LEDs, which do you think is the
Well, there's a gentleman in Australia by the name of Green who has a book on solar cells, and he's been a pioneer in making textured solar cells so that you grab all the photons and use them more efficiently in making solar cells. My ultimate lamp argument used concepts of solar cells in there. And Green has just published a paper in Nature where he says now if you turn that around and see the relationship between LEDs and solar cells, you texture the surface and you make silicon a better emitter. See, silicon and germanium emit light, but there's competition for the annihilation of electron hole pairs by loss processes. And the matrix element for the recombination process in silicon and germanium is slow, weak, compared to the 3-5s. So the 3-5s still have a big advantage, and the technology isn't quite there yet. Look, I've known about light in germanium and silicon since I was a little boy in the semiconductor industry. And in fact, there's a film on this here in the building by Pankov and Adler at MIT showing you light from germanium. But you're not looking at any of those, and people aren't building lasers out of them. In other words, if one of you bright young people can make me a laser out of germanium, you are instantly famous. if you can make me a laser out of silicon, you are instantly famous. To my knowledge, nothing like that has ever approached yet the 3.5. In other words, there are some things that still belong to the 3.5, and there are some things that belong to silicon. Silicon's fantastic because it's tough, it's got a good technology, it has this fantastic oxide. I failed to point out when I showed Bardeen's inversion layer that inversion layer is patented by Bardeen before the original transistor. That inversion layer patent is the CMOS. That inversion layer is how you make the switches in the chip. Why does it take us so long to do all these things? Because it takes that long to learn and to develop the technology. And you're talking about a technology that's still not there. The science isn't quite easy, and the technology isn't quite there. And in spite of Motorola's announcement here of the last couple of weeks that they have grown gallium arsenide on silicon, it remains to be seen what the data look like and whether we have any reason to believe what they're saying. So it's still a problem. None of these problems are solved easily. I don't think there is a problem, there's a solution right now to the question, a solution and an answer to your question. It's a good question. Silicon carbide lasers? Oh boy, that's a long story. That's a whole seminar. You know, that claim was made. That was in Time magazine. That was in publicity. John Bardeen and I had a little argument across the street, and he wanted me to work on silicon carbide lasers, and I said, John, you have to invoke some other physics. I looked for a year at visible spectrum lasers, semiconductors, and I said, no one on earth has seen as many as I've seen. And why won't these guys who claim to have a silicon carbide laser show that to my technician whom they're trying to hire from GE to Tyco in the Boston area? I said, John, invoke some different physics. He knew I had him. There wasn't any other physics. How? If my lasers in gallium arsenide phosphide, which are red, take more current, more cooling than Bob Hall, my colleague's gallium arsenide lasers, his are at lower gap, mine are at higher gap, and the silicon carbide guy comes along, and his crystal is indirect. The electrons are off in momentum space at a different place than holes, have a weaker recombination matrix element, and he goes to the green and blue and is going to run CW at room temperature. Wow, something's wrong. Now, here this many years later, people keep invoking that. I go after all this on a trip to the Soviet Union. I see some silicon carbide there, and these guys in a famous laboratory in the middle of Leningrad ask me about, they show me silicon carbide light emitters, and they ask me, is it true about lasers in silicon carbide? And I know it's not true, but you see that doesn't die fast when it's been in Time magazine and here, there, and everywhere else. Who are those writers to say? But at any rate, now it keeps coming back. It keeps coming back, and the science isn't there. Silicon carbide is a nice substrate for other stuff. But as a light emitter itself, it stinks for scientific reasons. See, that magic of the propaganda is still, we're buying into it.
Next question.
I'm sorry the answer took so long.
Any more questions?
I'm surprised you were asking a question about the old timers and who was nice and who was a son of a bitch and all that kind of stuff, you know. No. You know, and you have your own take on it, but the young people don't know.
Let me ask you a question. You have done a lot of interesting work, pioneering work, lasers, purity disordering, oxidation. Which one you feel most excited about?
Sean Lin, it's not the old ones that you feel excited about, it's the next one. when Jorez Alfyorov was in our group in 1970-71, and when he came to the country, when he came through customs, he was carrying a suitcase with a minimal amount of clothes and something else with a maximum amount of vodka. And the customs guy knows right away. He says, "Oh, you're a scientist." and so he can read English well, but he can't hear it well. And so I take him home, and Kay makes us a nice dinner, and and I produce some wine, and he brings all the vodka to my place, and I say, "Johannes, niet." No. And he says, "I can't drink it in my apartment by myself." He says, "I'm not alcoholic." So by the time we drink some vodka and by the time we drink some wine, boy, wow, that's driving me nuts. But one of the things there were many Cold War things that he told me and I told him that were supposedly secrets. but nevertheless, one of the things that always kept coming up was "ще одно," one more yet. One more item to work on. In other words, what you've done, you've done. It's okay. It's out there and all that kind of stuff. Why did Bardeen stop in Syracuse to see the light emitters? You see, the man has a Nobel Prize. He's into superconductivity and all that. What the hell would he want to stop in Syracuse to look at light emitters and lasers for? In other words, you see, there's another fascination in the next issue, the next problem. The young man who asked me about silicon carbide, maybe he's a genius and has the biggest trick on earth to do something with silicon carbide that none of us have thought of. That's exciting. In other words, it's the next problem, Shunman, not the old problem. The old one, we're tired of the old one. But we don't like people taking the old results and warming them up again and pretending that they're new.
Okay, let's thank the speaker.
Thanks.